Okay folks, welcome back into chapter 2, chemistry of the cell, and as you can see from the list here, quite a lot to do, and we're going to start out looking at some review for carbon containing molecules, so a little bit of organic chemistry, very basic, and then we'll look at the stability that arises from the use of organic chemistry. So just to review valence and bonding, remember the carbon atom on the left there has a valence of 4. That means it can form 4 chemical bonds with other atoms, and it's, remember, all these atoms are going to form the number of bonds they need to satisfy the octet rule. So carbon is most likely to form covalent bonds with other carbon atoms, with hydrogen, oxygen, nitrogen, not shown here but very, very important, also phosphorus. So remember that a covalent bond is when two atoms share a pair of electrons, and then if they're going to share 2 pairs of electrons, that would be a double bond, and if they're going to share 3 pairs, that would be a triple bond. So you can see here that the methane on the left has formed between a carbon and 4 hydrogen atoms, and we've got 4 shared pairs of electrons, so 4 single bonds. And so if we move over towards the right, we can see ethylene there, CH2CH2. The carbons are sharing a pair of electrons with hydrogen atoms to form single bonds, but then we've got a double bond that's formed between the 2 carbons in the ethylene, and obviously probably a bit more familiar are the double bonds that form between carbon and oxygen in carbon dioxide, and so that is also 4 shared electrons, 2 pairs of shared electrons. So electrons are shared between atoms to allow atoms to become more stable by their meeting the octet rule, which gives them a complete outer shell of 8 electrons. Okay, a little bit of new stuff now. May not be new if you've taken chemistry recently. Generally, the molecules that we look at in biology are stable because life likes stability, and so stability arises because of carbon bonds forming, carbon hydrogen, carbon nitrogen, carbon bonds. So these bonds are generally stable, and the stability is expressed in terms of bond energy, and that's the amount of energy that's required to break 1 mole of a given type of bond. It's not the amount of energy that's released when you break a bond, it's the amount of energy required to break the bond. So this is expressed as calories per mole or kilocalories per mole. Remember that calorie is the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. So kilocalorie is 1,000 times that much, so it's 1,000 calories. I'll give you an idea of the relative strengths of these. You can see the graph on the screen here. Carbon-carbon bond rolls in at about 83 kilocalories per mole. Carbon nitrogen about 70 kilocalories per mole. Carbon hydrogen lower down there at 99, higher up there at 99 calories per mole. And then obviously the double and the triple bonds are significantly stronger. And then you can see for the sake of relativity, hydrogen bonds are down there at about 2 kilocalories per mole, being a very weak bond, stronger probably only than van der Waals interactions, which we're not going to talk about right now. Why is this important biologically and in terms of cell biology? If these bonds weren't stable and they were exposed to radiation, then covalent bonds used to make biological molecules could break, and the most common form of radiation that cells would be exposed to would probably be solar radiation. And so you can think about this as kind of chemical selective pressure, if you like, and we see these bonds being used in biological molecules because they're not broken by the wavelengths we see in visible light. Now, if you do get down to UV and shorter wavelengths, now you can start to do some damage to molecules and to cells because there's enough energy in the short wavelengths you find in UV radiation to actually damage biologically useful molecules. But we see a lot of stability in biological molecules and in biological systems because radiation, mainly in the form of solar radiation, doesn't break those bonds. Okay, so that's all we're going to get into with this, nice and short, and I'll see you next time when we come back to look at a technique called mass spectrometry.